Thank you very much for coming in this late afternoon session. Welcome everybody. My name is Zoltan Porkolab, and this is a talk about debugging and profiling C++ template metaprograms. And in this project, got essential help with Zoltan Boroknagy, who is sitting here and will help me on questions and implementation details, and also from József Mialica, who is unfortunately was not able to come here. And as you see that two of us working for Ericsson Hungary, and the other two is related with Eötvös Loránd University. So, debugging and profiling C++ template metaprograms. Well, I've seen in the previous lectures that it's not too much space to explain what is C++ template metaprogramming. It basically, everybody has a fundamental knowledge about it. So I will just take it short. Well, then I try to discuss the possible debugging and profiling techniques of C++ metaprograms, especially two major possibilities. Instrumentation and the compiler support. Then I would like to introduce the template backend tool, which is our Clang-based template metaprogram debugger and profiler stuff. And then I will show how to use our two prototype front ends. One is for really debugging and visualizing template metaprograms. Other is for retrieve profiling information, instantiation times, and so on and so on. Then I will talk about a little bit about a vision how compilers could support more template metaprogram development itself. So there is an official definition of what is metaprogramming, and we know that since 1994 we have template metaprograms and lots of applications related. But whatever is the official definition, after 4 days here in the C++ Now conference, you might be confident that what are C++ template metaprograms for. Of course, compute factorial in some smaller possibility that we use it for Fibonacci or something like that. But really, we have a huge number of usage area of template metaprograms. We have compile time adaptations, different kind of optimizations, including expression templates, which are perhaps the first techniques, static interface checking, go back to 2000, the Erfurt C++ template workshop. It's lots of possibilities simulating language extensions, DSL embedding, and many, many other possibilities. We have the area of C++ template metaprograms. Basically, what is important from this is that nobody can claim that this is just a hobby of some nerd. It's a really application area for C++ template metaprograms around. And just my view about that. And I know that we have a solution, a nice solution in C++ 11. Still, I choose this example because in my C++ class at Eötvös University, I found this example as one of the best way to express that the motivation of C++ template metaprogram. So I used to ask my students that what should be the return type of these maximum functions to return the biggest value, the right type for the biggest value. And I usually promise them the best mark if they solve the problem, which is not a big risk, because we know that we cannot choose the type of the biggest value. because that's a runtime issue. And in a strongly typed programming language, we have a strict separation of compilation time when we decide the types, the constant values, and here we fix all these type-related issues when we compile the program. And on runtime, we might decide which is the biggest value on various algorithms. So there is kind of firewall between them. So, of course, that's impossible to solve. However, still, we can see that perhaps here, if this is a long and this is a short, well, it's better to return the long value here. And if this is a double and this is a short, then it's likely the double will lose less information. And even if we don't know, perhaps this is some input and it's not wired in the code, we don't know which will be the biggest value, we can see that which type should return. Unfortunately, the situation in C++ generic programming is not that easy, because when I design this maximum function, I usually have no idea that in which environment will be used. And I don't know whether T, S, or a third type would fit best for the instantiation environment, which will happen perhaps in a separate application years later. So what we usually forget, that we have another firewall between this kind of design time when we decide the return type of the maximum function and the actual compile, or in this case instantiation time, when we will see, or the compiler will see actually the real environment, those types who will replace T and S. So metaprograms, C++ template metaprograms, is a way how we can inject our algorithms from design time over that firewall to instantiation time. And I know that this is not the best choice, just to choose the longest, the biggest size, because there are a certain possibility that it's not the best return type, but still we are in a Turing complete sublanguage of C++, so we can choose arbitrary complex algorithm. So basically we can design our C++ template metaprograms here, which will be executed in compilation time, dependent of the real instantiation environment. So of course there is a certain difference executing an algorithm in runtime and in compilation time, and we know that what are these features in runtime and how we usually map this in compilation time features. As we usually think, template metaprograms are kind of functional programming paradigm, and well, of course we have kind of functions, meta functions. Basically they are types. Instead of values and literals, we have const, enums, const expressions. Data structures are simulated typically with kind of recursive types, data structures like type lists or MPL vector and so on. We have no classical branching, but we have pattern matching. We have no classical loops, but we have recursion, like in functional programming languages. We have no assignment at all. We have this kind of functional programming referential transparency. And well, for debugging issues, one of the biggest differences is that runtime programs usually depends on input or execution environment. However, compile time programs are usually deterministic. I say usually here because one of my students is now playing with random compile time programs seeding with the time macro. I don't really see what will the purpose of that, but it's an interesting experiment. So actually we have pretty good support in C++, starting from the compilers. We have heard Chandler's presentation about that, but we all use debuggers, profilers, and lots of stuff. You can all at least have number of perfect or almost perfect tools, many of them open source. Static analyzers, lint-like tools, debuggers, profilers, code compression tools, style checkers, program visualizers. So we have pretty good support on runtime C++ programming. So let me ask you to enlist a number of tools for supporting template metaprogramming. Well, that's the issue. We have almost 20 years using C++ template metaprograms, and we have still no have real feasible good tools. So basically we have for runtime C++ program support this, and this. And for compile time programming we have this. And how you can tell your boss to use template metaprograms in your production code if you cannot tell him that, okay, if there will a problem, I can debug it. If there is a bottleneck somewhere in compilation time, I can profile it. So we hardly can live without tools. Why? Why we need tools, especially for C++ template metaprograms? Well, all we know the reasons. C++ syntax is not designed for template metaprograms. Actually, as template metaprograms are rather functional paradigm, it would much better to use kind of functional programming language-like stuff. This is what Abel Shinkovich is working on in different ways. So this is why this Haskell-like stuff is going around again and again for C++ template metaprogramming. But even if the syntax is as we have, compilers are not optimized for detecting and reporting template metaprogram errors. I will show a few examples about that. And the other stuff is compilers are not really optimized for executing template metaprograms. I might think that situation is much better than that time when Todd Vertuisen wrote these measurements and issues about how bad internal structures exist for supporting templates. But even if there are kind of advantages in this area, these internals are a black box for the programmers. So we basically give the source to the compiler, and we have either some kind of syntax error, warnings, or a program which doesn't really do what we want. And of course, we have no idea what happens. We have not kind of printf facilities to follow the situations, or while I would really love static warnings for this purpose, but unfortunately there are no such things in C++ 11. And of course programmers have a much better experience in runtime programs than in template metaprograms. So we need tools to write our C++ metaprograms. Because it's everything fine, then it's such easy and clear are template metaprograms. Unfortunately, programming is a human activity, and this human activity may involve bugs. Okay, and when we have bugs, then we are in a unfortunate situation that we have to solve this in a short time, and we hardly can do this with proper tools. So just a few examples. This is just a missing semicolon, and as we expect, this won't be a huge problem. The compiler perfectly detects the problem and shows us that, hey guy, here you made a error here. I will likely fix it in 3 minutes and compiles it, and everything is fine. However, I might make other mistakes. Homework for the audience to detect which is my favorite editor. Okay? So this is a bit harder because the instantiation starts, okay, and when it goes down for the usage of factorial 0, and only then the compiler can catch the problem. Now, this is factorial as an example, but let's imagine a complex complex C++ template metaprogram when there are hundreds of lines, and you have to detect that what was the real issue. Actually, this clang message is still quite clear and helps to detect the problem. Okay, what other errors can happen? Here, the user starts to detect factorial -5, which we see will be an infinite recursion. And modern compilers catch it because there is kind of limitation of the recursive template instantiation. And if this exceeds, then we've got a pretty nice error message. Although in a more complex case, this is still hard to find. And well, our user might think that, okay, it's something was a small parameter for the compiler. Let's increase that. So let's try this. And, well, you see the result. So this was just a kind of light ontology of what kind of template metaprogram bugs we might find. You can see kind of relations to runtime programs like divide by 0 or infinite recursion can happen in runtime programs too. So the worst thing is not do these errors, because modern compilers gives better and better error messages. The worst thing is when there are no error messages at all, but your program doesn't do what you want. And that's actually the worst case in runtime programs too. For template metaprograms, you have even less chance to follow what's happened, and that visualization and understanding what happens in our program is still essential. So there was a number of efforts for this area. Debugging, profiling, and visualize tools. Go back for concept checking. Many attempts has done for warning generation, instrumentations, and also for profiling. We have attempts. This is not a full list, of course. So if somebody is here in the audience has not enlisted, I'm sorry for this. But still we have no real usable tools. So let's say that what are the requirements, what are the main issues for this kind of debugger and profiler stuff? for profiling in runtime, of course, we measure the running time. It would be logical that for compile time, we measure the full compilation time. Unfortunately, this includes such things like the preprocessing stuff, which can take a serious percentage of the analysis. Also, the code generation, which is perhaps a less critical factor. But the rest of the time, what are we, especially when we optimize for C++ template metaprograms, is really the parsing time. And that still has a number of components. Chandler told last year that the overloading resolution of the outputting operator is a serious part of the Google code base compilation time. But what we really are interested in the template instantiation times. And also, when we want to follow what happens in a template metaprograms, we try to follow the instantiation chain. Who started to instantiate whom, when it finished, what kind of parameters have been used. And as we have lots of interactive debugger tools in runtime C++ program support, we not really need this for compile time. Well, basically what we can do, run the metaprogram, so basically try to compile the code and make a kind of post-mortem inspection on that stuff. Still, in both cases, we would use kind of forward-backward, step-by-step execution, which is, of course, harder in runtime, especially the backward one. We would like to use breakpoints. We would like kind of filtering, like eliminated unwanted events. So perhaps we don't interested in the instantiation of the standard library components. And, well, it would be a good help to use kind of source code and instantiations visualization. So one of the earlier efforts targeted instrumentation. What's the idea here? Basically, if we can inject a special code snippet for the beginning of all, beginning and the end point of all template instantiations, and these code can generate kind of identifiable warnings, then running this compilation, we can get a kind of trace what happened. Basically, every time we instantiate a factorial with a certain number, then we compile these lines, and these lines emit warnings. And if we are clever enough, we can filter this information and get some idea how the template metaprogram was executed. And of course, you can do this instrumentation by hand, by a script, or by more complex utility. And what you have to be care that, of course, these inserted codes modify the source line. So now your messages related not the original source line numbers, but that you can handle too. Some history about this story. On 2006 Portland, in the Gypsy conference, we presented the first version of our Metaprogram debugger, template 1.0, which was based on this kind of instrumentation effort. What we did is use first the preprocessor, then we've got the preprocessor source. We used our own instrumentator, which inserted the warning generator code into every template at the beginning and end points of the code. But at the moment, we also make the file when we remember that which warning, all the warning has a kind of unique identifier, which warnings placed in which place. So from the warning messages, we were able to retrieve the necessary informations. And then we compile the code, we catch the warnings, some of them generated by ourselves, some of them was caused by the code or was even error messages, and then we would able to map back these warning informations to the original source. So this is what was the original code in black, and the green is the injected code. It was not too bad, even if it was based on wave. So even the C++ parsing was not absolutely perfect, but in most cases it was usable. And this kind of instrumentation is a really lightweight approach. It's not a huge effort to make that kind of stuff. You've got pretty good results. And seems easier to port than any kind of compiler modifications. Still, warning generators are very much depending on the compilers, and there are other significant differences, like in memorizations and other stuff between compilers. Unfortunately, there are a number of issues. First of all, to make a correct instrumentation, you had a pretty good parsing effort, and that's not trivial if you use kind of lightweight solution. The other problem is memoization. Most of the times, when a memoization happens, you've got only one time warnings, and any other time you touch this already instantiated class, it will be silent. You haven't got more warnings about that, so you lose significant information. Lots of issues there are with inheritance. We try to use this with GCC and other compilers. Typically, you have a separate event for the beginning and of the base class and the beginning and end of the derived class. Then you have manually stuff. Yes, please?
I found that you're really clever. It's possible to deal with inheritance.
Yes, so...
I figured out how to do it. Real pain.
Okay, so the comment was that it is possible to handle inheritance. Yes, we did the two, but it's an extra effort, and it's all again compiler dependent. So just not fun, you know. Also, it's not easy to port the warning generator, and you have to update it every time there is a new compiler version. However, the real issues coming from the profiler stuff. Even if you generate the warnings, how you put the timestamp on them, how you measure when they were generated. So if you just write your compiler, you put your compiler and piping the warnings to another process and try to put the timestamps. It's such a delay that basically invalidates your numbers. And as we measured, the warning generation itself is quite costly. We had experiences when the warning generation itself taken the 20-25% of the whole compilation phase. So there is a quite big distortion if you use this kind of stuff. So basically instrumentation is okay for debugging, mostly okay for debugging, but it's not easy to use it for profiling stuff. So in our belief is that a good quality template metaprogram debugger and special profiler requires compiler support. And we did a few attempts to modify GCC, generate warnings and put the timestamp from the warning generator part of the code of GCC and this kind of stuff, but basically it was not really successful. Well, GCC is first of all not really designed for this kind of reuse. Perhaps it was not clever enough for the better solutions. But we have Clang now, and this is much better, much friendlier environment. So we continue to template 2.0 based on Clang. So what is this stuff? It's a patch over Clang 3.2, and it modifies plenty of the schema and parsing infrastructure of Clang to detect and measure instantiations, memorizations, measuring memory consumptions, and put timestamps on the events. So basically, when Clang runs, and every time we instantiate, we start to instantiate or finish to instantiate a template, or we use memorization, we emit a trace for an XML format. And this trace has a detailed description that what happened, when it happened, and if there is an extra switch turned on, then it's also measured the actual memory consumption at that moment. And we also developed two front-end tools, a kind of visual debugger, where you can follow the source code, and also there is a graph to see the instantiations, and another tool to view profiler data, so instantiation times and so on. Unfortunately, we haven't finished the visualization of the memory consumption. That would be, I think, also very interesting stuff. Any questions up to them? Okay, so this is basically what we have. A patch for the Clang, which generates this trace, and this trace can be consumed by our two front-end tools, or I think that's the much more important stuff, that anybody can use this XML for further processing. And this is available. I don't want to say that we have 2-digit number of of users at the moment. We just finished the home page. But we know that some of the clients are really used it, especially thanks for those who give us feedbacks, are Joel and Albert Shinkovic and others who gave us important feedbacks. So you can do this too. Just visit this home page. There will be a short description how to install, how to use the tool. You can download this one single tar GZ, which includes the patch and the two front-end tools. You can download Clang 3.2 as usual, patch it, build it, and optionally you can build your front ends, which depends only on Qt and GraphViz. But I think that you might create fancy client stuff for that. Yes, please?
Question on previous slide. It show like you have interactive debugging visualizer. What does it mean? It means when you just stop debugging, stop compiler?
No. It's a quasi-interactive. Okay, so the question was that the interactive debugger and visualizer, whether it's interactive in the way that it really runs parallel with the compilation stuff, and when I set a breakpoint here, the compilation breaks here. Not yet. There are plans for that. But at the moment, what we have is we generate the trace, and we have a kind of post-mortem debugging. We call it interactive because it behaves like the usual interactive debuggers. You can step forward, backward, go to a break, set a breakpoint, go to a breakpoint, filter out unwanted events. I will show a few examples.
It's like it works with this trace XML file.
Yes, this is the really important stuff. If you have this trace, you can replay it as much as you want. You can write a Python script to utilize it. You can make a GraphViz picture on that. Okay, so let's see a few examples. At this time, of course, I use Fibonacci and not factorial. You have the patched Clang. You run it with the -template flag, and this will generate this fib.cpp.trace.xml. And from the previous programs, it's not that big. It's 123 lines and looks something like that. This is just an example that you see that, for example, is a template begin. It's a template instantiation stuff. It's well, of course, escaped from XML. It's fib5. Point of instantiation, this file, this source line, this character. We have the timestamp. At the moment, we use vault time, which can be discussed. But at the moment, we thought that this perhaps the best honest approach. And you see here that memory usage is 0. This is because we switched memory measurement as a separate activity and with a separate flag. It's switched off by default. From some Clang documentation, we read that it's not cheap, and that's not default. But of course, you can switch this on. So this is a sample of the trace, and this is the tool. We call it Templar, just to include the temp substring. Works like a usual tool. You open the trace, and then you will see the code. And then you start it. This arrows goes one step in the XML file forward or backward. So we are walking through the instantiation events. And well, we start here. And on the right-hand side, we draw the instantiation graph. And the orange means that that template started to instantiate. And then you can step by step can go. Well, it starts to instantiate Fibonacci 3. Here you also can see the trace, the instantiation stack. There is information what kind of event was this. You go down to Fibonacci 1, and then Fibonacci instantiation finished. So it became green, and actually it was a specialization, so we detect this as a memoization event. We go to Fibonacci 2, starts to Fibonacci 2, which goes down to Fibonacci 0, and so on and so on. I don't want to go one by one. It's worth to mention that we do not represent the memorizations in one node. We could, for a few experiments, shows us that here somehow it's more logical to represent the graph. You can discuss this, and there might be a different implementation for the visualization. And then Fibonacci 5 finished. Okay, you can also use breakpoints. So, for example, here you can enter a regular expression. Our breakpoints or filters are basically regular expressions. So you do a breakpoint for Fibonacci 1. And that means that your trace will go down to the beginning of the instantiation of Fibonacci 1, which is a memoization event. And if you have no more breakpoints, then you will run on the rest of the stuff. Again, these graphical utilities are rather samples how you can utilize the XML information. Your student can do it better in 2 weeks, especially if this is a thesis for him. It's 1 week enough. Yes, please.
Cannot break down a line.
Sorry.
Cannot break down a line.
Can you break?
A line.
You mean here?
Or maybe somewhere within the template.
What you do is you put breakpoints on regular expressions. So you do not do. Okay. So the question was that can we do a breakpoint can we break in a line? What these breakpoints really are simply XML nodes. Okay. So we have a series of XML nodes with starting and finishing events of instantiations.
Also, so there is a file position. You already know where those are. I mean,
you want to say that, okay, I want to make a breakpoint at this certain point.
Yes.
We didn't do this at the moment, but you can. Of course, it means that you have to. Well, you have either to enter an exact point, which is in the XML file, okay, because otherwise we won't find it, or we have to maintain the information that certain template instantiations happens in which points, which I know that Clang provides with, but it's a different stuff, and we didn't bother with that at the moment. So at the moment, we do not make breakpoints on positions. We do breakpoints on template events. Other questions? Okay. Well, here's a seriously modified version of the Fibonacci. I use an include and print out. And you see the difference. Okay, of course, from the IO stream, the sender library and the who stuff, a number of template has instantiated. So when now you start to use a step-by-step debugging, you've got a number of classes, instantiations you are not really interested in. Or you might interested in this stuff, but perhaps you want to skip some of them. Filters are exactly for this reason. You can enter here a regular expression again, and those XML nodes in the trace matching this expression will be skipped. That's so simple. And of course, you can use multiply regular expressions. And of course, with regular expression, you can use a negation. So it's pretty flexible. However, it's not necessarily the most convenient. So after a few filters, I will be able to step my real stuff. That's pretty useful, especially if you use, let's say, MPL library and you trust MPL library and you are not really interested in what happens inside the MPL stuff. You are really want to learn what your stuff does. This kind of filter is quite good. Profiling data. We have two kind of version of that. One of them simply enlists the instantiations in a time order. So this is this take the most time to instantiate, or perhaps a bit more useful to view the stuff by names. So, for example, you can see std gnu. How? This is fib. This should be mine. Okay, you can see here that our Fibonacci stuff used for instantiation. Again, I'm sure that your students can do hundreds of different applications based on this idea, but you can start to do this. Yes, please?
That will show you not the addition of the times, but the one that took the longest? The top level?
Yeah, it seems for me, yeah. I'm not sure this is correct, but we can do summarize here. We should do summarize here, perhaps. So the question was that this fib here is the longest, and the answer is, unfortunately, it seems yes, and it's likely a bug or a feature which is not really fits for the expectations. Okay, that's it. You can also switch on the memory profiling stuff. And in that case, we also measure the memory consumption of the compiler in every time when we emit an XML node. And we have no front-end application from that, but you can draw beautiful graphs on this graphics or other stuff. So how it is implemented? It's the most stupid way, and that's perhaps the safest and the easiest stuff. At the beginning, we allocate a vector big enough, and every time we have an event, we just put a new node into the internal buffer. We do not outputting anything because it would be a distortion. If this size is not enough, which might happen, then of course you might put a parameter, template trace capacity, to increase this. Well, alternative approach that you simply, when your buffer is full, you simply emit all the nodes and measure the time you spent with that, and you simply destruct that time from the next outputting, next measurements. So there are a number of possibilities. Up to now, that was pretty enough. We flush at the end of the compilation, and we measure the stuff on that way that we did kind of zero measurement, and so with and without this modification, and we measure the minimal distortion, which is not surprise. We just take some nodes in memory under compilation, and all the output goes at the very end of the program. So if you use time utility, for example, you will see a huge number of distortion, but that's not really affects the real measurement stuff, because that's just the outputting at the end of the compilation. Okay, the real measurements about the real class instantiations will be more or less adequate. What happens if your compilation stops because of the errors we seen before? Well, in normal way, if the clang exits in normal way, so it's not really aborts, we made the output. And it doesn't matter whether we have a begin instantiation event in the XML, but there is no finalizing the instantiation event in the queue. Who cares? Okay. You can still use the graph visualization. You can, of course, the measurement. Well, the instantiation time won't be measurable. The only issue is that we've seen when the clang aborts for any reason. And that's a problem, because then we do not emit anything. We are planning a kind of safe mode when we flush every event immediately. Of course, that will destroy the profiling informations, but still we have proper debugging information what went wrong. Again, please download, install, and use it. It's not hard to use it, and we are really happy for any feedbacks. Yes, please.
So do you need a successful compile in order to get a useful XML output? Or can you debug a failed template instantiation? We can debug failed template instance.
So the question was that can we get information, reliable information on those cases when the compilation was not successful? Yes. The only issue is that when the compiler itself aborts. If there is no matching pairs for the beginning and end instantiation events, it doesn't matter. Okay, its XML structure is not about the containment of the instantiations. It's about the events. And if there is no matching events, well, who cares? still we can use this information. And some vision at the end. You see, that's not magic. It was an effort we did in a best effort way. Parallel lots of other activities. And if for us, basically, outsider of the compiler world, was possible to make this kind of information retrieval, how easy and how precise information could be retrieved if the compiler supports this by the compiler stuff. Okay, and it's not something like the template closing mark which takes 10 years to implement. You know, it's much simpler. It's just a few points what the compiler implementers very much knows, and they can emit this kind of XML format or any other kind of XML format. And why not make the same kind of format, or at least some kind of compatible formats? And then all of us can profitize from this information. It's so little effort could be from the compiler writers, and so big advantage would be for the C++ communities. Yes, please.
You contact about this vision with other vendors, for example, Microsoft.
So the question was whether I share this vision. I am here now. How much of the audience has connected some compilers? Okay, so that's it. We think that a real precise profiler debugger requires compiler support. We implemented this template 2.0 stuff as a patch over Clang 3.2. It's downloadable. You can use it. We provided 2 sample front ends for it, and we hope that we will use it. And please give feedback, as it would be very important for us to learn and to make its tool even useful. So, thank you very much. Yes?
Will you be submitting the patch?
Sorry?
Will you be submitting the patch to Clang?
Honestly, I don't. So, question was that whether we will submit this patch to Clang, and we would happy for that. I don't know whether the quality is good enough. I was not even sure that which kind of copyright should it be. It's just Chandler told me that perhaps this LLVM copyright is the proper. Yes, please.
So I think you should submit it to Clang. I think that it needs some pretty specific work before it goes into Clang. I'm happy to talk with you about what changes would be good to do before you mail it out afterward. I think that I'm moderately confident that the Clang community will be very happy to have and support long-term the ability to output this type of XML file. I don't think there are going to be any serious objections to it. I don't know how they could object to it very seriously. It seems totally reasonable to me.
So the comment was, yes, you should. Okay. Thank you very much.
That's a good summary.
Okay. Questions?
I think a more useful thing is, like what you said, makes the XML formatting standardized.
Well, the comment was that perhaps the most useful stuff to make some kind of standardization of this XML format. Yes, but we have only a few users, very, very small experience in that. So that takes some time to learn that what would be the best information package. This is, let's take this as a version 0.9 or something like that, and if there will be a few volunteers to make hex and their compilers, we will learn that what will be the best format. Yes, please.
So, especially since C++ 11 expressions template metaprograms, or metaprograms in C++ in general often consist of a lot of overloaded functions, templates that have enable if clauses, and then the bug you have in your metaprogram is that it suddenly chooses the wrong overload or the one you want that doesn't work and no other works either. Have you considered basically extending this to trace overload resolution?
Actually, Joel told us these same things for us. The question was that, to summarize it, that most of the C++ metaprogram errors especially in C++ 11 somehow related with wrong overloading resolution. This is basically the stuff you taught. So whether we go for that way, it would nice, but we have even less experience with this. So this is exactly what compiler vendors can do in a perfect way. Yes?
I think that going this way is turning your tool more into a C++ compilation debugger, because you go far more than just template metaprogramming. So that's, I think, obviously one huge task on top of what you already have. But
So,
I think it could be actually useful for a lot of use cases where the problem is not the template, but what we do next to them to make them work.
so Joel told that he also thinks this is a useful direction, but the limit is the up in the sky somehow. So it's a huge task, and well, again, I think that this is somehow we should left for the compiler vendors. If we catalyze something in this direction, we are really happy for that. Any other questions, comments? Then thank you very much, and please use the stuff.